In this problem, we are given the following circuit diagram here. We are also given that our current is equal to this, and we need to find the time domain voltage across the 20 ohm resistor. Now, to do this, I can notice that all of our impedances, meaning this impedance, this impedance, this impedance, and this impedance, once we add these two together, are in parallel. And since they are in parallel, that means the voltage across all of them is the same. So the voltage across this 20 ohm is V, and the voltage across this capacitor is going to be the same V. And then if we combine our two impedances back here, I'll just draw a line right here and a little animation right here and say that this impedance is also our V because it is all in parallel. And remember, voltages in parallel are the same throughout. Now we are going to combine these two impedances. They are in series, so all we need to do is add them together, and that is going to be the impedance of this part right here. First, we need to change this into the Z equation. So we're going to have Z of our inductance equal to J times our omega times L. This is the formula to convert it. We're going to have J times our omega, which is 50,000, so we'll have 50,000 times 40, and since this is microhenries, we need it in henries. We're going to have a -6, or 10 times -6. And if we do all this, we're going to get that our Z of L is equivalent to J times 2. And so the total impedance here is going to be 1 plus J times 2. Now we can use a node voltage equation and select one of the nodes here. I'm going to select this node because we actually have a current going into it that'll help us solve it. We know that our current is 20 with an angle of -20 degrees. So we're going to write a node voltage formula for this. There is current going into our node, so our current is negative. We will have a -20 with a -20 degrees. And next we are going to add our V because we know we have current going down this way. And then we're going to have current going down this way, and as well current going down this way. Since they all have to add up to this node, we are just going to add them together. So after this current is here, we're going to have a plus V over 20, and then we will have a plus V, and we need to convert this capacitor, which I have not done yet. And the conversion for a capacitor is that we will have a Z of C equal to a -J over our omega times C. We know our omega is 50,000, so we will have a -1 divided by our 50,000 times our capacitor, which is just 1 microfarads. We need to convert this to farads, so we will have 10 to the -6. And this will give us a Z of C of -J times 20. So we will have that our V is over a -J times 20. And for the last parallel part, we will have our V divided by our 1 plus J times 2. And this will all be equal to 0. From here, we can combine the like terms for our V and then move our current to the right side. From here, I'm going to simplify this further by dividing everything in our V. I divided the first two out. Now for this next part, what we're going to do is convert the bottom part, which is our 1 plus J2, into polar form, and the same thing with our top, so that we can divide them. To convert this into polar form, we're going to use the equation that our Vmax is equal to the square root of our real number squared plus our imaginary number squared, and that our angle is equal to tangent of -1 with our imaginary number on top and our real number on the bottom. And if we do this, we're going to get a 1 with an angle of 0 degrees, and then we're going to get a 2.24 with an angle of 63 degrees. Both of these are approximate as well. And this will be set equal to our 20 with an angle of -20 degrees. From here, we are going to divide our real numbers and then subtract the denominator from our numerator angle. And if we do this, we are going to get 0.4d5 with an angle of -63 degrees. Now we need to convert this back into rectangular form so that we can add it with this part right here. To convert from polar to rectangular form, we are going to use the equation where we have our number, parenthesis, cosine of our angle, plus J times the sine of our angle, and then parenthesis. And from this, we're going to get a 0.2 minus J times 0.4. And we can add all of these together now, and also move this underneath our angle right here so that we can divide them and find our V, which is the voltage. Also, I just realized I made a mistake with this part right here. It should not be a negative because we brought the j up top. When you bring the j up top, or basically whenever you switch its position from the bottom to the top, or if it's on the top from the top to the bottom, you make it a negative out front. So you'll have a negative j when you switch it. That means because we bring this j up to the top, we are going to have a plus because we have this negative out front, and when we move the j up, it'll be a negative j. So all of these will need to be switched to a plus. And if we do all that, we are going to get this for our equation. Now we are going to convert our denominator into our polar form and then divide these. We are going to get approximately 0.4 with an angle of negative 54 degrees. And from here, we are going to take our numbers and divide them. We are going to take our denominator angle and subtract it from the numerator angle. And if we do this, we are going to get for our V max, or magnitude, 46.5. And then for our angle, we are going to get 34.5. And this is the answer in how you would go about solving for this problem. If you want more network analysis problems, there's a playlist in the description, and if you want notes that cover the entire course, they will also be below the like button in the description.